Greetings and welcome to the complete lecture for Chapter 14 of Chemistry 223. And in this chapter, we will look extensively at how acids and bases provide a valuable tool in the world of the chemist. Acids and bases create a lot of energy when done correctly, and we'll see how this energy can be used in a lot of different ways. To talk about how acidic or how basic something is, we'll also use what's called the pH scale. And that picture there on the right will show some of the values of pH. pH more or less goes from 0 to 14. And finally, along the way, we're going to see how acids and bases are around us all the time. Almost everything we eat is somewhat acidic, and most of the cleaners we use are somewhat basic. So without further ado, let's see what this chapter has to offer. The theory we're going to use primarily, and especially in this chapter, for acids and bases is called the Bronsted-Lowry theory. And in the Bronsted-Lowry theory, or just Bronsted theory as it sometimes is called, an acid is a compound that donates a proton, an H+, to another compound. And a base is a compound that accepts that proton from another compound. And there's lots of examples of Bronsted acid-base theory around us.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
This is a reaction between ammonia, NH3, which is actually basic, as we talked about back in Chem 221, and NH3, a base, reacts with water, H2O, to make ammonium, NH4+, and remember ammonia and ammonium are different, and hydroxide. But what I'd like you to look at in this particular reaction is how water here is donating an H+. Like on the product side, water becomes hydroxide, which is water without the H+. So the H+ is donated to the NH3, that makes water an acid. But if NH3 is accepting that H+, that means that NH3 is a base. So on the product side then, NH3 becomes ammonium, which is NH3 plus an H+, and you're good to go. However, notice that this reaction has equilibrium arrows, the double-sided arrows we talked about in the last section. And like all equilibrium, you can think about them as reactants going to products as well as products going to reactants. So now let's consider ammonium reacting with hydroxide. And if you think about it from that perspective, the ammonium is donating an H+ to the OH-, so ammonium becomes ammonia. So ammonium is an acid, and the hydroxide here is accepting that H+ from the ammonium to make water, so hydroxide here is a base. So when it comes to equilibrium, you can have acids and bases on both sides of the reaction, and that's going to be one of the things we talk about in this section. So in this reaction, ammonia is a base and water is acting as an acid. And the ammonia makes ammonium, which is an acid, and the water makes hydroxide with the base. So notice that a base makes an acid on the other side, and an acid makes a base on the other side. The NH3, NH4+ combination is called a conjugate pair. And a conjugate pair is just two chemical species which are related by the loss or the gain of an H+. So you add H+ to ammonia, you get ammonium. You take an H+ away from ammonium, you get NH3 ammonia. So they go back and forth. The other conjugate pair in this equation, of course, would be water and hydroxide. You give up an H+ from water, you make hydroxide. Hydroxide gets an H+ and it makes water. So we have two conjugate pairs in this reaction. Ammonia, the base, and ammonium, the acid, as well as water, the acid, and hydroxide, the base. This is another reaction of an acid-base reaction. This is hydrogen carbonate, HCO3-1, and it's acting as an acid here because HCO3- is giving up an H+ to become carbonate, CO3 2-. So notice that carbonate and hydrogen carbonate are conjugates. HCO3- is the acid. It has more H+, so it gives up the H+ to the base, which accepts it, CO3 2-. But water is also making its own conjugate pair. Water here is acting as a base. It's accepting the H+ to make hydronium, H3O+, an acid. And you can think about it, of course, as hydronium, the acid, giving up an H+ going to a base. So a couple of things here. Conjugates are really important. Conjugates are just two chemical species where you're either adding or subtracting an H plus to give the other one. One of them will be an acid, the one with more hydrogens. The one will be the base, the one without less hydrogens. Also notice here that water is acting both as an acid in the first example with ammonia, as well as a base here in hydrogen carbonate. So water is an example of a compound that can be both an acid and a base. It just depends on what else is around it. So this is a question you might see. It says, which of the following is not an acid-base conjugate pair? And the punchline here is that conjugates are related by an H plus or minus. You add the H plus to the base and it makes the acid. Take away the H plus from the acid and it makes the base. And hopefully you can see right away that it's answer A, which is not a conjugate, because HClO has a hydrogen, chlorine, and an oxygen. And its conjugate is not going to be just chloride, because conjugates are related by H plus. So the conjugate of HClO would be ClO minus 1, and the conjugate of Cl minus would be HCl. Those are how conjugates work, so it wouldn't be the other one. But if you look at B through E, they're all plus or minus an H plus. So HF there on B, take away the H plus, it becomes F minus plus an H plus becomes HF, you're good to go. The last one there, E, HNO3, take away an H plus, you make nitrate, NO3 minus 1, add an H plus to nitrate, you make nitric acid.
Without the addition of any other substances, two water molecules can interact with each other to produce a hydronium ion and a hydroxide ion by transfer of a proton from one water molecule to another. This process is called autoionization.
We've seen so far how water can act as an acid, i.e. with ammonia, NH3. It can also act as a base, i.e. with hydrogen carbonate. So water can be both an acid and a base. And when water's by itself, it actually does what's called autoionization. And that means that a small number of molecules will come together to make H3O plus and hydroxide. So at all levels and all concentrations, you're going to have some hydronium and some hydroxide at any temperature. At 25 degrees Celsius, this value has been studied quite extensively, and the value of the autoionization is 1.00 times 10 to the minus 14. This value is much, much less than 1. That means there's not a lot of products being made, and in this case, the products will be H3O plus and hydroxide. But it is an important number, as we'll see. Kw, that 1.000 times 10 to the minus 14th, that's a number you're going to want to know / memorize. We'll use that here in a little bit. The idea here is that autoionization of water happens at all temperatures, and some water will always break down into hydronium and hydroxide, which is kind of interesting. If Kw equals hydronium times hydroxide, and that equals 1.000 times 10 to the minus 14th, and if water is the only thing that's breaking down, then every two waters will make a hydronium and a hydroxide, and the hydronium and the hydroxide concentrations will be the same. So instead of saying Kw equals hydronium times hydroxide, because they're equal, you could say Kw equals hydronium squared or hydroxide squared, either way. But if you're curious as to what the value of hydronium or hydroxide is, take the square root of that Kw. So the square root of 1.00 times 10 to the minus 14th equals hydronium, and that's going to be the same number for the hydroxide. That comes out to be 1.000 times 10 to the minus 7th moles per liter. So at room temperature, 25 degrees Celsius, the concentration of hydronium and the concentration of hydroxide, 1.000 times 10 to the minus 14th. You really should memorize Kw. That's going to be something we'll use quite a bit in this section, and if you can just start getting in your brain, the better. So here's a question you might see. It says a solution has a hydronium concentration of 1.0 times 10 to the minus 18th. What is the hydroxide concentration? So at this point, what's important to remember is the Kw value, because Kw, which is 1.000 times 10 to the minus 14th, that equals hydronium and hydroxide. So if you take Kw, divide it by that 1.0 times 10 to the minus 8th moles per liter, you will find the concentration of your hydroxide. So if you did the math, this comes out to be 1.0 times 10 to the minus 6 moles per liter. That's the value of hydroxide when hydronium is 1.0 times 10 to the minus 8th. And notice if you multiply those numbers together, you should get Kw. Kind of cool. Now, the amount that an acid ionizes reflects on how strong the acid or base is. And first we'll talk about strong acids. Strong acids dissociate 100% into hydronium and a conjugate base. So for example, if you have a solution which is labeled HNO3AQ, you honestly don't have HNO3AQ. What you have is almost pure hydronium. So if it was 3 molar HNO3, you'd have 3 molar hydronium. And you'll also have the conjugate base of HNO3, which in this case happens to be nitrate. So that's kind of an interesting thing. Strong acids break up 100% into their conjugates and hydronium. Nitric acid is about 100% dissociated. There's no nitric acid present. It's only hydronium and nitrate. And so usually what people will do is use single-sided arrows here. This isn't an equilibrium. This is a one-way trip. It's difficult to go back. That's why it's cool to write the one-sided arrow. Weak acids, on the other hand, do not dissociate completely into hydronium and a conjugate base. Maybe they have 1 in 10,000 molecules that does this, but certainly not a lot of them. So this is an example of nitrous acid. Now, nitrous, HNO2, is different than nitric acid, which is what we saw in the last time, HNO3. Nitrous acid does dissociate. It reacts with water into hydronium and nitrite ion. However, the concentration is quite a bit less. So we're not using the one-sided arrows here. We're using double-sided arrows. And the equilibrium constants for these weak acids are called acid ionization constants, K sub A. Acid ionization constants are really only relevant for weak acids, and Ka in this case is equal to H plus times nitrite divided by HNO2, nitrous acid. Sometimes H plus is listed as H3O plus, same thing. In this case, the author just went H plus times nitrite divided by HNO2, and that's fantastic. Bases have a similar kind of process. There's strong bases and weak bases. The strong bases dissociate 100% into the hydroxide and some kind of conjugate acid. So sodium hydroxide in water actually doesn't have anything really to do with the water necessarily, but the NaOH does break up. It makes OH minus, which is really cool, and also a sodium plus ion. And you can see that they're AQ, so that means that they're floating around or something like that. Sodium hydroxide is about 100% dissociated in water. There's no NaOH. It's only hydroxide with some sodium maybe. And you really should use the single-sided arrows here to represent what's happening with the strong bases. Weak bases do not ionize 100%, just like weak acids, and there's a whole bunch of these out there. So if you have a weak base, for example ammonia, it reacts with water to make hydroxide and also ammonium. So the water goes to hydroxide, the ammonia goes to ammonium, and you are good to go. This expression right here then is called a Kb expression, a base ionization constant expression. It's products over reactants. We're not putting liquid water in because, oh my gosh. But anyway, we will put in the ammonium, the hydroxide, and divide it by the ammonia. In Chem 223, there are 5 strong acids and 3 strong bases you really have to know. We're going to encounter thousands upon thousands of acids and bases as chemists collectively, and almost all of them are weak. However, there are these 5 strong acids and 3 strong bases, so make sure you know them. So the 5 strong acids are nitric acid, HNO3, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, and hydrogen perchlorate, or hyperchloric acid, which is what it's usually called, HClO4. Those are very strong acids. And so if you had a mole, say for example, of perchloric acid, you would have a mole not of perchloric acid, but actually of hydronium and also the perchlorate ion. Now the strong bases, those 3 strong bases, super important. Sodium hydroxide, potassium hydroxide, lithium hydroxide. And basically for all other bases, we can assume that they will just be weak bases. They won't be strong bases like these. So again, I highly recommend you memorize the 8 strong acids and bases, 5 acids, 3 bases. And there's a lot of uses for this beyond just this discussion, by the way. You can assume that all other acids and bases are weak unless I tell you otherwise, but it should be pretty mellow.
When nitric acid, HNO3, encounters a water molecule, it forms an acidic solution by donating a proton, the H+ ion, to the water to form a hydronium ion and a nitrate ion. Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
So bases, once again, will take the H+, acids will donate the H+. Another thing about acids and bases, acids always create hydronium, and bases always create hydroxides. So that's another way to tell if you have an acid or a base. But generally what I do is I look at the reactants to products, and the conjugate species with less hydrogen will be the base, and the conjugate species with more hydrogen will be the acid. Now, Kw at room temperature, 1.00 times 10 to the minus 14th, and you can use more sig figs if you want, that's fantastic. But we can use this understanding and the idea that Kw is equal to hydronium times hydroxide to calculate hydronium and hydroxide at other concentrations. So as an example of this, let's say we have 0.0010 moles of sodium hydroxide and we place it in a liter of water. Well, let's calculate hydronium and hydroxide from there. Now, the reaction we're looking at, 2 waters going to hydronium and hydroxide. Now, if this was Le Chatelier's principle and we started adding in hydroxide, a product, we would predict that the reaction would shift to the left, to the side with the more liquid. So what that means then is it moves to the left, your hydronium concentration is going to go down. So this will be less acidic because you have less hydronium, and the reaction will shift to the left. So the hydronium here is going to be less than 10 to the minus 7th because you have a strong base. And what you should do is figure out an ice table for these kind of things as well. You'll only have hydronium and hydroxide. The hydroxide starts at 0.0010 moles per liter, or 0.0010 molar. They're both going to go up by X. All right, you can't have hydronium be 0 or negative, so it must go up by a little bit. So that's going to make it plus X for each of them, and then equilibrium, hydronium will equal X, and hydroxide will be 0.0010 plus X. You can let those equilibrium parts, let them equal to Kw. Kw equals X times the quantity 0.0010 plus X. And this reaction as written right now is a quadratic formula because you'd end up with X squared plus 0.0010X minus Kw equals 0. And that's a totally cool way to solve it if you have a solve button on your calculator, for example. However, because the X, which is the amount of hydronium made, is going to be so much less than 0.0010, all right? I mean, it was already 0. It's going to go up a little bit, but it certainly isn't going to go up that much. So what usually is done is you can ignore the plus X. That little plus X can often be ignored. Well, if that's the case, then hydroxide is 0.0010 molar. So you end up solving for hydronium. Hydronium equals Kw divided by 0.0010. And it does come out to be a small number, 1.0 times 10 to the minus 11th moles per liter. So in the last problem, we found that hydroxide was 0.0010 moles per liter, and hydronium was 1.0 times 10 to the minus 11th moles per liter. So both small, but the hydronium, of course, is especially small. Chemists consider this solution to be basic because the amount of hydroxide, the actual number, 0.001, is greater than the amount of hydronium, the 1.0 times 10 to the minus 11th. So in this case, scientists would consider this solution basic. So more hydroxide means base, more acid hydronium means acidic. Chemists are easier, though, with using what's called the pH scale. And pH is just a transformation you can make on your hydroxide and hydronium to give you better values. So pH equals minus log the H3O plus concentration is a pretty important equation. It represents a way to quickly get just a number for the amount of acids that's present. And you always have to figure out hydronium, but it works for bases as well as it does acids. It's a pretty cool relationship. In a neutral solution, we saw that hydronium and hydroxide were both equal to 1.0 times 10 to the minus 7th moles per liter, and that's cool. What is the pH of that, Dr. Russell? Great question, random student in the back of the room. pH is minus log hydronium. So minus log 1.0 times 10 to the minus 7th, that gives you a pH of positive 7.00. So 7.00 is the pH of neutral solutions. Nothing else has happened with them. They're just totally neutral, and it's pretty cool. Soren Sorensen was the first person to create the pH scale. I think chemists like the little O with the line through it, so they just like to show off or something, but still pretty cool. Okay, so here we want to find the pH of a 0.0010 molar sodium hydroxide solution. No problem. So what we need for figuring out pH is we need hydronium, not hydroxide. And earlier we calculated how the hydronium would be 1.0 times 10 to the minus 11th moles per liter. That's the number we need for pH, not hydroxide, but hydronium. So minus log 1.0 times 10 to the minus 11th, that comes out to be a pH of 11.00. What this means then is that in general, a basic solution will have a pH greater than 7. So in the sodium hydroxide solution we looked at earlier, the hydronium was that 1.0 times 10 to the minus 11th, which is a lot less than the 0.0010 number we started with. So more hydroxide than hydronium, that means the solution is going to be basic, and we can see by the value of pH of equal to 11, you bet it's going to be basic. Anything greater than 7 should be a base. Now, neutral solutions technically are just for pH of 7, or pretty close on it, depending on who you talk to. But the closer you are to 7, the more likely it is to be neutral. And the acidic solutions have pHs which are less than 7. They're going to have more hydronium than hydroxides, and literally the number will tell you if you have more hydronium or more hydroxides. pH is less than 7, more hydronium, so that's acidic. pH is greater than 7, will have more hydroxide. Those solutions are basic, and right around 7, it'll be neutral. In this question, we have a solution with a pH of 10.5, and we want to know, is it acidic, basic, or neutral? It might be lame, it's true, but that's not a valid answer here, so just ignore that. Anyway, literally look at the value of pH, and pH is greater than 7, i.e. 10.5, those are going to be basic. If your pH is less than 7, for example, 5.5, that would be acidic, and if it's equal to 7 or very close to 7, that's when it's going to be neutral. So pretty easy to find out. In the picture on the right, we have a Diet Coke solution being analyzed by a pH meter. A pH meter is just an electronic device that allows you to find how acidic or basic something is. And you can see in this example with that pH probe in the Diet Coke, pH comes out to be 3.12. So because the pH here is less than 7, we would call this Diet Coke acidic. And most compounds and drinks that we eat and consume, most of them are actually a little bit acidic. Now, because the pH equals minus log of hydronium, we can calculate how much hydronium is actually present. And the hydronium, like all things in square brackets, will be in molarity. So let's calculate the moles per liter of the hydronium. So what you want to do is take the anti-log of both sides. Now the pH is 3.12, and as you can tell, if you put the negative on the other side, you're going to get 10 to the minus 3.12 equals hydronium. Now the anti-log for base 10 is just 10 to the x. So 10 to the power of log H3O plus is just H3O plus. On the other side, you do something to 1, you have to do it to the other side. So 10 to the minus pH is where the 10 to the minus 3.12 came from. This comes out to be 7.6 times 10 to the minus 4 moles per liter of hydronium at that particular set of conditions. In this problem, we have a pH of 4.50, and we want to solve for the hydronium, the H3O plus concentration. No problem. So hydronium equals 10 raised to the power of minus 4.50 when you figure it out. And in your calculator, and this is definitely a job for your calculator, this comes out to be 3.2 times 10 to the minus 5, or answer B. So that's what's kind of cool about this. It's easy to find hydronium from pH, and all other things will follow shortly as well. Now, we haven't talked about sig figs and logarithms yet, and we need to do that real fast because we're going to use a lot of logarithms. So in general, when you have a logarithm and you want to take the log of a number, you're going to use n sig figs for every n decimal places after the decimal. And it's easier just to show examples of this. So here are 3 examples of using sig figs. The first 2 are outright logarithm calculations. Now the log of 3.07 times 10 to the minus 3, that's a 3 sig fig number. So we want to record digits 3 places to the right of the decimal. So minus 2.513 would be the correct number. And you can try this in your own calculator. You wouldn't raise it to minus 2.6 or something like that. You want to keep 3 sig figs, which means 3 digits past the decimal. Now log 1.1 is a 2 sig fig number. So you can see there's 2 red numbers to the right of the decimal, which is kind of cool. And then finally 10 to the minus 3.12, the 1 and the 2 are going to be our sig figs. We're doing an anti-log. Remember, all the anti-log is the number of sig figs past the decimal. So in this case, that would be 7.6 times 10 to the minus 4. Nothing you can't do, a little bit weird, but anyway, now you know what's going on. Most food and drinks are slightly acidic, and most household cleaners are somewhat basic. So up in that chart in the upper right there, you can see the pH values of different compounds. And the acidic part, i.e. the numbers less than a pH of 7, things like water, coffee, orange juice, wine, stuff like that. Lime juice is pretty acidic. On the other hand, the things that are greater than 7, the basic parts include things like ocean water, baking soda, milk of magnesia. A lot of the household cleaners have ammonia, NH3, so that's there. Sodium hypochlorite, NaOCl, is actually a base as well. So lots of examples on both sides, and we'll see more and more of these as we go through the course. We saw earlier how pH equals minus log of the hydronium, essentially minus log of H+. But in reality, you can have any kind of px scale where px equals minus log the concentration of x. So if you know how much you're starting with, then you can find the px for that value. We're going to talk in a little bit about pKa. Now, we saw some Kas earlier. We're going to talk more about Ka, and pKa is minus log of Ka. We'll come back to this in a little bit, but just kind of keep that in mind. pKa equals minus log of Ka. POH is another thing we'll use. Now, POH is related to the hydroxide. So POH equals minus log of the hydroxide concentration. And if you wanted to find hydroxide, you'd go 10 to the power of minus POH, etc., etc. Kw equals hydronium times hydroxide, which equals the Kw value 1.000 times 10 to the minus 14th at room temperature. Well, maybe you want to find something out from there. If you take the negative log of both sides, you get negative log 1.000 times 10 to the minus 14th. And that equals minus log of H plus and minus log of hydroxides, because hydronium times hydroxide, if you do the logarithm of that, it comes out to be negative numbers. But anyway, at the end of the day then, you end up with this expression, minus log of 10 to the minus 14th is 14. That equals minus log of hydronium, which is pH, plus minus log of POH, all right? And so if you know these kind of things, you can find one from the other as long as you're about room temperature. And if you ever do studies where you're away from room temperature, you may have to double think your math to make sure that you're right, stuff like that. pKa, which is minus log of Ka, plus pKb minus log of Kb equals 14. And that's kind of cool. Now remember, Ka is the equilibrium constant for an acid. Kb is the equilibrium constant for the base. And most of the time they're under 1, so they're reactant favored. 14 equals pKa plus pKb. That's going to be pretty important to us coming up. We have a solution with a hydronium concentration 3.2 times 10 to the minus 5. What is the POH? Okay, hydronium is H3O plus. OH minus is hydroxide. So we need to translate the hydronium concentration into hydroxide to answer this question. And there's a couple different ways you could do it. What I would probably do here is I would first solve for hydroxide, because Kw equals Ka times Kb, but Kw also equals, as we saw, hydronium times hydroxide. So if hydronium is 3.2 times 10 to the minus 5, and we want the hydroxide ion concentration concentration, then Kw divided by 3.2 times 10 to the minus 5 should give you the hydroxide value. And once you have hydroxide, minus log of hydroxide will give you POH. So let's look at how that works out. So here's Kw divided by hydronium, 10 to the minus 14th divided by 3.2 times 10 to the minus 5, and all of that equals the hydroxide concentration. So once you have hydroxide, then minus log of hydroxide will give you POH, and you can tell we're good to go on that, which is kind of cool. A way to check yourself is that the pH of a basic solution should be basic, i.e. the pH should be greater than 7. And you can see on that list up there, C, D, and E are all acidic or neutral, so that's not very helpful. Now, A could be a base, but that would be pretty powerful. Most bases fall off a long time before 14, and that value is 18, so that seems a little unreasonable. Litmus paper can be used to tell if you have an acid or a base in solution. Now, earlier I showed a picture of a pH probe, and honestly, that's probably a better way. However, litmus paper will do the same thing. And the litmus paper has colors associated with it. So if you have kind of like a red color or that kind of off-orange color in the upper left-hand corner, that means you have an acid. On the other hand, if you have kind of a blue-purple kind of color, that means you have a base. So we're going to go through some relationships here to think about how these acid and base things kind of operate. An acidic solution will have a pH less than 7, all right? That's no problem. But a pH less than 7 means acid, and that means acid, the hydronium, will be greater than the hydroxide, the base part, all right? So hydronium will be a bigger number, and hydroxide will be a smaller number. And POH being really small, even for these kind of things, POH is going to be very, very large. It's not going to be very strong. Remember that low values of pH and POH mean strong. So a low pH would be more acidic. A high POH would be less basic. That's kind of how this part works out. For a basic solution, it's the opposite. For a basic solution, you'll have a large pH, a pH greater than 7. But bases mean you don't have a lot of hydronium, so that'll be low. But bases do mean you have a lot of hydroxide, so no problem. And then finally, if you have a lot of hydroxide, your POH will be down. So that's kind of how this works in terms of acids and bases. What you need to remember is that Kw, hydronium times hydroxide, that's always going to be a constant. And for us at room temperature, 25, it's 1.00 times 10 to the minus 14. So that'll help you to understand how these things go around. And also remember that pH plus POH equals 14. So if pH goes down, POH is going to go up. If POH goes down, pH is going to go up, etc., etc. All weak acids have conjugate bases. So we saw hydrogen carbonate earlier had carbonate, no problem. And likewise, all weak bases have conjugate acids. So ammonia has ammonium. There's all kinds of examples of that. These weak acids and weak bases don't ionize very much. It's usually less than 5%. So for example, one molecule in 20,000 molecules or so, that's kind of what you'd probably expect for one of these weak acids and weak bases. So Kas for acids and Kbs for bases are used a lot in this section. Almost all the Ks are less than 1 and quite a bit less than 1. So here's some examples. Acetic acid with acetate, those would be conjugates. Acetic acid is the acid and acetate is the conjugate base. Likewise, ammonium is a weak acid and ammonia is a weak base. And bicarbonate is a weak acid, and carbonate is the conjugate weak base. So these are just examples of acids and bases that are weak and how they interact with each other. Now, for any acid, any weak acid, Ka is going to equal hydronium, H3O plus, times the conjugate base A minus, divided by the concentration of your weak acid. And there are no exceptions to this. All Ka expressions will follow. All Ka expressions will have a hydronium. But if you have a base, the second set there, bases react with water, it'll make the conjugate acid, BH plus, and some kind of base, in this case hydroxide. So Kb would be the conjugate acid times hydronium times the value of the conjugate of the weak base. If you have a Ka for a weak acid and you look long enough at the Kb for the conjugate base, something really interesting happens. Now for the weak acid, Ha plus water makes hydronium and the conjugate base, and that's not a big deal, but that would be a Ka expression. The corresponding Kb expression, if you start with a base which is already negative, the base reacts with water, it ends up making H plus as it pulls the H plus off water, and you end up with hydroxide. So these are two conjugate Ks. You could have ammonia and ammonium for Kb, and you could have ammonium and ammonia for the Ka above. Either way, it's going to happen. But what's cool, though HAs, the weak acids, the conjugate base A minus, and will all cancel out. And you'll be left with two waters going to hydronium and hydroxide. And sure enough, that's the expression for a Kw. So Ka times Kb equals Kw as long as they're conjugates. And if you extend this out, Ka is equal to minus log of Ka, and Kb is equal to minus log of Kb. So when you multiply them together, it's like they become kind of like family, which is kind of cool, I guess. Anyway, neither here nor there. So what this means for us, if you have conjugates, Ka times Kb equals Kw, and that can be really empowering. And if you minus log all that stuff, you end up with pKa plus pKb equals 14. And there's a lot of examples where sometimes it hasn't worked out, but here it certainly has. pKa plus pKb equals 14. The Kb for nitrite is 2.17 times 10 to the minus 11th. Let's calculate the Ka for nitrous acid. Now, this problem would be tough, except that nitrous acid is the acid and nitrite is the conjugate base. They're conjugates of each other. If you take away an H plus from HNO2, you end up with NO2 minus. You add an H plus to NO2 minus, and you end up with HNO2. So in this case, since we have Kb and we want to find Ka, let's use Kw equals Ka times Kb and solve for Ka. So if you do that, sure enough, 10 to the minus 14 divided by the Kb, 2.17 10 to the minus 11th, the overall value here comes out to be C, 4.61 times 10 to the minus 4. That's the value of Ka for nitrous acid. In our problem set, we'll use a table like this. This is a table that lists the acids and bases with their strengths. And there's a couple of things worth pointing out. So first of all, at the very top of the acid side, which is on the left, several of the acids just say large. And those are considered super strong acids, and they don't really have a usable Ka. So you can kind of just ignore them. But then right after H3O plus, we end up with H2SO3, HSO4 minus, et cetera, and it goes all the way down. What's really cool about this is that the strongest acids are at the top and the weakest acids are on the bottom, which is kind of a neat thing. On the other hand, the bases are on the right-hand side. They start off with the very, very weak bases, and they progressively get larger and larger until you get to the very large values of K. So for weak systems, one of the weakest systems you'll have would be H2O there, 1.0 times 10 to the minus 14th. Hydrogen sulfate right under it is also pretty weak. It has a Ka of 8.3 times 10 to the minus 13, so pretty small, okay? This also, if you look at it long enough, lists conjugates directly apart from each other. So if you look, for example, at hydrofluoric acid, which is right there, fluoride is right across from it, and they're related by a conjugate. So what that means for us is like the Ka value for HF times the Kb value for fluoride, that should equal Kw, 10 to the minus 14. And that'll work for all of these, which is pretty neat. So at the bottom, hydrogen phosphate there is 3.6 times 10 to the minus 13. That's the Ka. Let's multiply it by the Kb for phosphate, 2.8 times 10 to the minus 2. It should come out to be pretty close to Kw, which is pretty cool. So this table is great for looking at Ka values and Kbs. And you don't have to memorize any of these. I would give you the values on quizzes and exams, but just know how to use them in case you run into them. K, the equilibrium constant, gets bigger as you have more and more product. So it says here which is the strongest base, but all of these Ks are less than 1, okay? So that means all of them are weak. A mole of these won't create a mole of the base or anything like that. However, K is starting to approach 1, which is the kind of line of demarcation, if you will, between something being acidic and something basic. So the strongest base here is going to have the biggest Kb, because strengths of bases are described by how much hydroxide comes off, and you're going to have more hydroxide with a bigger Kb value. So if you look at those numbers long enough, it's carbonate, 2.1 times 10 to the minus 4. That's going to have the strongest base, because even though it's weak, it's going to create more carbonate than any of the other species that might be doing carbonates and hydroxides. So the biggest Kb is going to be the strongest base, and the smallest Kb will be the weakest base. So we would expect carbonate to have more hydroxide available than any of the species up there, and that's going to make it the strongest base. Again, acid strength is determined by hydronium, and base strength is determined by hydroxides. Now, Kas will have hydronium as a product, so as one goes up, the other one goes up. Your strongest acids will have the biggest Kas. And the same thing for bases. The strongest bases will have the biggest Kb, and there's all kinds of examples of how this works out. Now, it's kind of cool to find out what the value is for Ka and Kb. You will never have to look those up. You can always use those table, or I'll give you the information. No problem. Chemical reactions proceed from the stronger acids to the weaker acids, as well as from the stronger bases to the weaker bases. Now, in terms of equilibrium constants, that means it's going to go from the larger Kas to the smaller Kas, as well as from the larger Kbs to the smaller Kbs. So, for example, if you had there in the middle H2CO3 carbonic acid, that has a Ka of 10 to the minus 6. And that's not too weak. However, it's a lot weaker than, for example, HF, hydrofluoric acid, which is 10 to the minus 4. So we would say that HF is the stronger acid, and H2CO3 would be the weaker acid. We're just comparing the magnitudes of Ka. And the same thing on the bottom, but for Kbs. So bigger Kb means more basic. So if we're comparing phosphate on the right side with ammonia, phosphate has a bigger Kb, 10 to the minus 2. It should be more basic there when it comes to NH3. So here's a reaction. We want to decide if this reaction is mostly on the right or mostly on the left. Will it be product favored or reactant favored? And these kind of questions can be kind of tough, except that I want you to remember the 5 strong acids and the 3 strong bases. Now, the three strong bases: sodium hydroxide, lithium hydroxide, potassium hydroxide. And the 5 strong acids: nitric acid, perchloric acid, HBr, HI, and HCl. And lo and behold, if you look at that problem, we've got hydrochloric acid right there. Strong acids and strong bases always push the reaction to the opposite side. So in this case, HCl is a reactant. It's going to push this reaction to the product side big time. It has nothing to do with carbonate. HCl is like a hunter killer. It's going to move and get rid of it as soon as you can. So in this case, because of the presence of the strong acid, we would say this reaction lies on the right. Strong acids and strong bases always push towards the opposite direction. Pretty powerful. We can use all of these pieces of information to calculate the pH of weak acids and weak bases. And so, for example, for acetic acid, CH3COOH right there, you can find the value of the pH if you understand what Ka is all about. So for acetic acid, Ka would be H plus or hydronium, either way is fine, times the conjugate base, which is acetate, and you'll divide by the acetic acid. And if you understand Ka, you can find hydronium, and hydronium will lead you to pH. Now for bases, we'll use the Kb expression, but it's the same idea, which is kind of cool. Now to find out how much hydronium is there, you can use one of those pH meters on the right. And what I want you to see, there was a little video that played initially, but what I want you to see is that as the concentration of the weak acid increases, so we went from 0.0001 to 0.003 to 0.06 to 2 molar, you can see how the pH needle there got more and more acidic as the concentration goes up. So higher concentrations, more acidic, which means lower pH. And we'll see that in this section. So for acetic acid, which I'm going to abbreviate as HOAC, HOAC is a common abbreviation for acetic acid. I'm not totally sure why, to be honest, but anyway, that's how it goes, and I'm just the messenger. Anyway, acetic acid will react with water to make hydronium and the acetate ion. And let's assume that we have a 1 molar solution of acetic acid. That's all we need to calculate the concentrations of the weak acid, the hydronium, the conjugate base, and even the pH. All right, so let's use an ice table to do that. We'll set up the ice table, reactants on the left, products on the right. Don't include water because it's a liquid. When you do that, you can see what the values come from. Now, acetic acid started at 1 mole per liter. That's the only piece in the initial line. Hydronium and acetate are considered to be 0. But you can't have zeros at equilibrium, so hydronium and the conjugate base will both go up by X, while the acetic acid goes down by X. So at equilibrium, we got 1 minus X and X for hydronium and the acetate ion. By the way, that note there, water creates hydronium, creates 10 to the minus 7th moles per liter hydronium at room temperature. And usually that's so small that it doesn't affect the amount of hydronium we're looking at in these problems. Sometimes super precise things will need to take into account the hydronium from water, but we won't have to in this class, so just FYI. The Ka is a number you can look up in the table we talked about. It's also in problem set 3. And for acetic acid, it's 1.8 times 10 to the minus 5. So that equals hydronium times the conjugate base acetate divided by the acetic acid. So that would be X times X for the numerator, or X squared. We'll divide it by the acetic acid, started at 1.00 and went down by X. Now, right now, this is a quadratic formula. You're going to have Ka times 1 minus X equals X squared, and you'll end up with a quadratic formula like we talked about last time. And there's nothing wrong with solving that. If you have the solve button on your calculator, it makes it pretty chill and pretty easy, honestly. However, a lot of times there is a better way to do these problems. So if you have a problem like that, you really should check to see how small X is going to be relative to the initial concentration. Now, X is going to be the amount of hydronium, and the initial concentration for us in this problem is 1.00 moles per liter. So if you can assume that that little minus X is small, you can literally cut it out, all right? Just ignore it, because 1.00 minus the X by sig figs and all that stuff is still going to be 1.00. So if that X is very small, that makes this problem a lot easier, because then Ka, 1.8 times 10 to the minus 5, that equals X squared divided by the concentration of the acid, 1.00, and that's easy to solve, because X then will equal the square root of Ka times Ca, and the square root of Ka times Ca would be square root 1.8 times 10 to the minus 5 times 1 mole per liter. And so that's a lot less math to do than a quadratic, and this is why sometimes people like doing it. The approximate expression, which ignores the 1.00 minus X, it ignores the minus X part, you get Ka equals X squared over Ca, where Ca is the concentration of your acid. When you solve for X, X is literally equal to the square root of Ka times Ca. So as you can see there, we're raising it to the 1/2 power, which is like square rooting. It's 1.8 times 10 to the minus 5 times 1, and the square root of that. So when all is said and done, X comes out to be 4.2 times 10 to the minus 3 moles per liter. And minus log of that number gives you 2.37, which is kind of cool. Now, we don't have to worry about the acetic acid part, because in acetic acid part, it's basically just equal to 1.00 moles per liter, so no problem. On the other hand, this can be a pretty powerful thing. Even if you are a TI expert and you love using the solve button and all that kind of jazz, this can be pretty cool because it just takes less time to enter in your calculator. Now in the lower right there, it says I did this in the calculator. I used the quadratic formula. I got two values of X, 0.0042 and negative 0.0043. And you don't want to use negative numbers in chemistry. It just doesn't work out very well. So in this example, X is 0.0042, which kind of makes sense using our stuff right here. Pretty cool. Hydronium equals square root Ka times Ca if the conditions are right, if X is small enough relative to the concentration of the acid. A way to check this, if 100 times Ka is less than Ca, then you can let hydronium equals square root Ka times Ca. Or if you rewrite this real fast, the pH of a weak acid equals minus log square root Ka times Ca. And that's actually a much nicer way to calculate pH than to go through the ice tables to find hydronium, and then minus log of hydronium equals pH. You can absolutely do that, but it is more work. So if 100 times K is less than C, use it, and pH equals minus log square root Ka times Ca. Try it yourself on some of the problems and let me know how it goes. Here's an example where we have a formic acid solution, and formic acid has a Ka 1.8 times 10 to the minus 4, so a little bit bigger than the Ka for acetic acid in the last problem. And also notice here we're using a really dilute solution, 0.0010 molar is pretty small. And then the last example, we had a very concentrated solution, 1.00 molar. But anyway, we can use this information to calculate the pH of the formic acid solution. If you use the approximate method, hydronium equals square root Ka times Ca. So square root, parentheses, 1.8 times 10 to the minus 4 times 0.0010, that ends up with a value of 4.2 times 10 to the minus 4 and the pH of 3.37. However, if you use the quadratic formula, you get slightly different numbers. Hydronium comes out to be 3.4 times 10 to the minus 4, and your pH is 3.47. So on problems like this, you really need to check if 100 times K is less than C. And 100 times K in this problem is 100 times 1.8 times 10 to the minus 4. That's 1.8 times 10 to the minus 2. And that is not less than Ca, which is 0.0010 or 1.0 times 10 to the minus 3. So in this problem, 100 times K is greater than Ca. And if that happens, you really should use a quadratic formula, and that's what the values are given down below there. So this is just an example of how it doesn't work all the time, but if you check for 100 times K being less than C, it should be good to go. Here's a reaction with a weak base ammonia, 0.010 molar ammonia, Kb 1.8 times 10 to the minus 5. Let's find the pH. Okay, this problem is similar to the last one, except that pH from hydroxide is a little different than pH from hydronium, but same things. So what you do in this problem is set up the ice table. We're starting with 0.010 molar ammonia and no ammonium or hydroxide. So at equilibrium, you'll have minus X for ammonia and the 0.010, while X will equal ammonium and the hydroxide value. Kb for this expression, 1.8 times 10 to the minus 5. Ks are always products over reactants, so that would be ammonium times hydroxide over ammonia. That would be X times X, or X squared, divided by 0.01 minus X, all right? And once again, this is the complete expression, but you can probably imagine that we'll check it here and see if we can do an approximation where we can remove that little minus X by the 0.010. So just like with the acids, you can check the bases too. If 100 times Kb is less than Cb, you can ignore that little minus x. So 100 times 1.8 times 10 to the minus 5, the Kb, is 1.8 times 10 to the minus 3. And that number is less than Cb, 0.010, which is 1.0 times 10 to the minus 2. Now, Cb and 100 times Kb are getting closer to each other. However, 100 times K is still less than C, so you are welcome to get rid of that minus x. So if you do that, then x squared equals Kb times Cb. X squared equals 1.8 10 to the minus 5 times 0.010. So the square root of both sides, it gives you just x, which is hydroxide. Square root of Kb times Cb comes out to be 4.2 times 10 to the minus 4. And that equals the concentration of hydroxide and the concentration of ammonium, which is pretty cool. We assume that ammonia stays the same at 0.010 moles per liter. Now, you can kind of check yourself with these approximations. So if the original concentration minus the amount that you calculate, hydroxide or hydronium, is about the same as the original concentration, then you're good to go. And this one is pretty close to 0.01, so it's okay. And like before on the quadratic, you can solve these kind of questions. I did that below. And you can see how x came out to be 0.00042, or 4.2 times 10 to the minus 4. And the other x value is negative, and that just doesn't fly. So everything seems to be pretty good here, and we are good to go. Okay, so on the last slide, we figured out the hydroxide is 4.2 times 10 to the minus 4 moles per liter, and that is pretty cool unto itself. However, we want to calculate the pH. And again, in this problem, we're starting with hydroxide, not hydronium, so we need to somehow translate hydroxide to hydronium to find the pH. Now, what I would probably do is I would find POH first, and that's just equal to minus log of the hydroxide. So minus log 4.2 times 10 to the minus 4 gives you 3.37. That's pOH. So pH plus pOH equals 14, which is what we saw earlier. So 14 minus 3.37, 10.63, and we are good to go. A lot of times, I like to use this expression. So just like with the weak acid, we saw that pH equals minus log square root Ka times Ca, as long as 100 times K is less than C. Well, for weak bases, 14 plus log square root Kb times Cb is actually a pretty nice approximation as well. So instead of going like hydroxide to POH to pH or something like that, or hydroxide to hydronium and then pH, which would have worked fine too, you can do it all in one step. So I do recommend checking out these short and quick and dirty kind of versions of these equations, but of course it's up to you. This is an overview of the 4 equations that I use for strong acids and strong bases. Now, strong acids and strong bases dissociate 100%. So when you have like 0.1 molar HNO3, that means 0.1 molar hydronium. So for those, the pH is literally minus log the concentration of the acid, or minus log hydronium. For strong bases, because that hydroxide term, you go 14 equals pH plus pOH, and you can solve it from there. So 14 plus log concentration of the base will equal the pH. So again, there's no Kas or Kbs for strong acids and strong bases. We only worry about those down below when we get to weak systems. Now, for weak systems, assuming 100 times K is less than C, pH equals minus log square root Ka times Ca. And for weak bases, it would be pH equals 14 plus log square root Kb times Cb. And again, these 4 equations help me out a lot. That's why I'm sharing them with you. I encourage you to memorize them so you don't have to think about it too much. Good to go. Let's think about now for a second what would happen if you had equal moles of strong acids and strong bases together. And they call this equimolar. If that's a term you hear, that's what it means. Now, equal moles of strong acids and strong bases mean you have equal moles, for example, of HCl and sodium hydroxide, a strong acid and a strong base. And you know what the 5 strong acids and 3 strong bases are, don't you? Go back and look at them if you don't, because they're really important. But anyway, anyway, all the strong acids and strong bases, if they're equal moles, will create water and some kind of salt. In this case, sodium chloride. It's the leftovers outside of water. That's what the salt is. But here's the punchline. The salt is not going to have any effect on pH, and water is just pH of 7. So a strong acid plus strong base should always result in a pH of 7 if the moles are equal, which is kind of interesting. Now, if you have equal moles of weak acids and strong bases, you would think that you'd have a pH of 7 as well. However, it's really interesting because the strong base and the weak acids have knocked themselves out because there's nothing of them left. But the weak acids turn into their conjugate bases. And bases, being the operative word, bases have pHs greater than 7. So if you have equal moles, weak acids, and strong bases, those two wipe each other out, and the conjugate base comes back to haunt the pH. So the pH will be greater than 7 for equal molar weak acids and strong bases. And likewise, weak bases with strong acids have something similar. What happens in these cases, the acids totally knock the weak bases out. However, the weak bases create a conjugate acid. Acid being the operative word, acid solutions will have pHs less than 7. So in a little bit, we're going to focus on these equal molar parts of a titration, as we'll see. And if you have a strong acid, strong base, the equal molar part will have a pH of about 7. On the other hand, the weak acids and strong bases will have pHs greater than 7, and weak bases and strong acids will have pHs less than 7. We'll come back to this here in a little bit. I'll show you how important this can be. This is kind of an overview of all these places. Now, equimolar has a fancy name with titrations called equivalence. So when you hear equivalence, you should think equal molar. It means the mole of the acid and the mole of the base are equal. And down there in the table, you can see there's 4 different combinations. You got strong acid plus strong base. And on the right-hand side, if you look way over there, you can see that the pH is going to be equal to 7. On the other hand, a strong acid and a weak base, if they're equal molar, the weak base is totally knocked out, but its conjugate acid starts to kick in. And acids being acidic will have pHs less than 7. So strong acid plus weak base equimolar or equivalence, those are going to have pHs less than 7. Weak acids plus strong bases have a similar process, but the weak acid has been destroyed. Its conjugate base is now the operative piece, and bases have pHs greater than 7. So that will be one way to tell if you have a weak acid plus a strong base. The pH will be basic. If you have a strong acid and a strong base, the pH should be equal to 7. Now, there are conditions where you can look up weak acid and weak base titrations, but honestly, those aren't very helpful, and we're not going to focus on them. But if you had to do this kind of question, you could do it. You would compare the Kas and the reactant side to the Kas on the product side, and the bigger Ka will push to the smaller Ka. And yes, you could do it for Kb. The bigger Kb on the reactant or product side will push towards the weaker one. It'll be the same answer for Kas and KBs. But that's more than we'll go into, but that's what you would do if you had that kind of problem. Salts, or ionic compounds, will be neutral in water if the hydronium and hydroxide concentrations are equal. And for some cases, that can happen. But what happens a lot of times with salts, which are basically just ionic compounds, is either the cation or the anion will be a little bit acidic or a little bit basic. So the question we're going to ask here, let's say we take some random salt, MX, and add it to water. Will it create an acidic solution or a basic solution? Now, ammonium chloride will be the first thing we'll think about. And ammonium chloride has a chloride, which I've made in purple there, as well as ammonium, which we'll tackle here in a little bit. So if you think about chloride, chloride could, in theory, react with water. It would take an H plus from water to make HCl, and it would leave hydroxide in its place. However, ding, 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 there's one of the strong acids, HCl. And those strong acids and strong bases do not sit well on the opposite side of the arrow. They like to push the arrows in the opposite way. That's what it means to be strong bases and strong strong acids. So what this means is that if hydrochloric acid were to form and hydroxide, it would only be for like a millisecond because the HCl will quickly react with hydroxide and remake the chloride in the water. So all the strong acids and strong bases push to the other side. So chloride is not going to have an effect on pH because if it did make HCl, which would create some hydroxide, it would just be there for a millisecond before it pushed it back towards the reactants. Chloride is considered a neutral ion. It has no effect on pH. All conjugates of strong acids and bases do not affect the pH of the solution. And this is also another reason why knowing that crazy list of strong acids and strong bases is really important. Because the conjugates of the acids, chloride, bromide, iodide, nitrate, and perchlorate, as well as the conjugates of the strong bases, sodium, potassium, and lithium ion, all of those do not affect the pH of the solution. So this is also kind of cool. If you want a solution which is pH neutral, i.e. pH 7 from water, you could use things like potassium chloride. Potassium comes from KOH, chloride comes from HCl. They're not going to affect the pH. You could also use, say, lithium nitrate. Lithium from lithium hydroxide, nitrate from nitric acid. That'll create a neutral pH solution as well. But there's also ammonium in ammonium chloride. So let's think about what happens with ammonium. Now, ammonium with water will react. It'll make ammonia and hydronium. And this is something you might have seen already. Now, ammonium is actually a weak acid. It's creating hydronium, which is the product of an acid, and its conjugate base is ammonia. So ammonium is actually a moderate acid. I'd like to say a weak acid, but that sounds kind of lame. So it's just a moderate acid, all right? The ammonia itself is actually a little bit stronger than the ammonium, but that's neither here nor there. But the important part here is that ammonium and ammonia, those are both weak systems. Ammonium is a weak acid, all right? And weak acids will create a little bit of acid, like not a huge amount, but it will create a little bit. So here's the big picture. If you put ammonium chloride in water, the chloride won't affect the pH at all, but the ammonium will make the solution a little bit acidic. And if that's okay, then no problem. But what happens a lot of times is you don't want to have a pH effect. You want your solution to just be neutral. So knowing then that ammonium chloride will create an acidic solution can be really important. And it's the ammonium's fault. It's not chloride. Chloride could care less. It's just hanging out in the sidelines saying, yeah, you go ammonium. But it's the ammonium here which is creating the slightly acidic solution. So this is what chemists think about. They need to know the effects of the pH created when you make salt solutions, when you make something with a cation and an anion. This table lists ions which are neutral, ions which are generally basic, and ions which are generally acidic. And I want to look at the neutral ones because all of those neutral ions are essentially the conjugates of strong acids or strong bases. Now the anions look very familiar. Chloride from HCl, nitrate from HNO3, etc., etc. No effect on pH. Now the cations I've wanted you to know are lithium, sodium, potassium. Those are the three strong bases we're looking at. Now honestly, magnesium hydroxide, which is where the Mg2 plus comes from, and calcium hydroxide and barium hydroxide, barium 2 plus, those are all more or less strong bases as well. But I don't care if you know those. All right, I just want you to know the simple ones. But those are also going to be neutral pH parts if you need to have a solution. Now, the basic anions are all negative, all right? So more often than not, if you have to guess, the basic anions will be the negative ones, all right? That's not all the time the case because you can see under the acidic column there's some negative anions as well that are acidic, but they all have hydrogen, so that's another kind of thing to guess, but anyway, it's not easy. But anyway, they all have an effect on pH though, and that's important. Now, aluminum's kind of a weirdo. Aluminum aluminum can be a base and it can be an acid. So notice that aluminum is a base under the cations, and aluminum can be an acid there under the cations as well. So it's very strange. But I would like to highlight here how transition metal cations generally create acidic solutions. So like iron 3+ is notorious for making your solution a little bit acidic. Most transition metals will do that. We'll talk about this later, but just realize in the back of your mind that most transition metals will make an acidic solution. And there's ammonium that we saw earlier. Because ammonium is a positive ion, it will create a slightly acidic solution. So here's a question. Will 0.1 molar sodium carbonate solution have a pH which is less than, greater than, or equal to 7? It's asking us basically if it's acidic, less than 7, basic, greater than 7, or neutral, equal to 7. So to answer a question like this, you have to break sodium carbonate down to the cation and the anion. And sodium, Na+, that's the conjugate of NaOH, a strong base. So the Na+ is not going to affect your pH, no problem. Carbonate, on the other hand, is not the conjugate of a strong acid, strong base. So we would suspect that carbonate will have an effect on pH. That's going to get rid of the neutral answer here. And most of the time, the negative anions will be somewhat basic. So carbonate, for example, likes to grab an H+ to become hydrogen carbonate. That can only happen if it's basic. So that's why I would guess here that answer B would be right, because carbonate, like most negative anions, is probably going to have a base effect. And if you look back on that list, it certainly is. Now, another way to answer this question is you could look up carbonate for a Kb or a Ka on the table of acids and bases. And Kb is listed there, 2.1 times 10 to the minus 4. It's actually a fairly strong weak base. 2.1 times 10 to the minus 4 is a pretty large Kb overall. So this should have a pH which is greater than 7 when you place it in water. And again, the sodium isn't affecting anything. It's the carbonate here. Sodium carbonate, the sodium plus water, no effect on pH, neutral. Sodium is the conjugate of NaOH. But carbonate in water will create hydrogen carbonate and hydroxide. The Kb for the carbonate, 2.1 times 10 to the minus 4. So let's say we wanted to find the pH of a 0.10 molar solution of sodium carbonate. No problem. You could set up the ICE table. We initially have 0.10 moles per liter carbonate. We don't have any hydrogen carbonate or hydroxide initially. Carbonate will go down by X. The other two will increase by X. So at equilibrium, 0.10 minus X for carbonate and X for the other two. So just like we saw earlier, you would set all of these equal to Kb. So that would be X times X, or X squared, divided by 0.10 minus X. Now 100 times Kb we should check and see if it's less than concentration of the base. And 100 times Kb is like basically taking the 10 to the minus 4 and adding 2 to the exponent. So 2.1 times 10 to the minus 4 times 100 would be 2.1 times 10 to the minus 2. And 2.1 times 10 to the minus 2 would be 0.021. And that is less than 0.10. 0.10 would be 1.0 times 10 to the minus 1. So 100 times K is less than C. We are justified in pulling out that minus X. So if you do that, then X equals square root Kb times Cb, it comes out to be 0.0046. Now, notice on this one, I did solve for the exact values using a quadratic formula in my calculator, and I did get positive 0.0045. So it's amazingly close to 0.0046, but obviously it's a little bit different. Now, the quadratic formula does give better values. However, 100 times K is less than C, so I would use the approximation as well, and I would call the difference 0.0046 to 0.0045 as just scientific scientific kind of issues. It's the doubtful digit. That last digit is the most uncertain number when you make a measurement. So this isn't a big deal to me. That's why 100 times k less than c absolutely works here. But remember in the back of your mind that quadratics are a better way to go. If the hydroxide is 0.0046, minus log of that number comes out to be 2.34. And pH would be equal to 14 minus pOH. So 14 minus 2.34 comes out to be 11.66. So this solution is basic. No problem. If you wanted to, you could use 14 plus log square root KB times CB. And honestly, this way is so much easier. You don't need ice tables and pOH to pH and all that jazz. What I would do in this example, 100 times K is less than C, like we talked about. So 14 plus log square root 2.1 times 10 to the minus 4, the KB, times 0.10, the CB. And that does come out to be 11.66. So this is a huge time saver if you're comfortable with it. It's a little weird to go 14 plus log square root, parentheses, et cetera, but if you can get the 11.66, you got this down. You're going to get a high grade on the next test. Sorry, I couldn't resist throwing that in there. Crazy instructors. Transition metals are almost always acidic, and why that is that they undergo what's called hydrolysis. This is an example of a copper transition metal, copper 2+, and this copper is surrounded by waters, but what happens is another water comes in and it extracts one of the H pluses from one of the waters connected to the copper. So if you look right about here, there's a hydroxide. The water stole that H plus and relatively easy from the water to make just a hydroxide. And in the process, then you end up with hydronium. And hydronium is an acid. This is why most transition metal solutions are slightly acidic. Aluminum does this too, which is amazing, but it's the transition metals mostly. So if I were to ask you if a solution, say, of, cobalt 2+ in water was acidic, basic, or neutral, cobalt 2+ is usually going to be acidic. So just kind of FYI on that. You can actually find Ka values. Not all of these will probably be in our table, but you can find Kas, and if you have a Ka, it's very likely to be acidic. Will a 0.1 molar iron 3 chloride solution have a pH which is acidic, basic, or neutral? All right, well, again, big surprise, iron is a transition metal. And iron, the transition metal, will have a pH which is acidic. That's going to give you a pH which is less than 7. Now, I totally glossed over the chloride because, again, chloride is the conjugate of a strong acid, HCl. Chloride has no effect on the pH, but wow, the iron will. Iron will undergo this hydrolysis to make an acidic solution. We've been looking so far at what's called monoprotic acids. Monoprotic, mono is one, single proton acids. And these are by far the most common. So monoprotic acids would be things like HCl, HF, HNO2. They only have one H plus that's able to be ionized and be acidic. This means that they'll only have a single Ka value as well. However, there are quite a few what are called polyprotic acids. Polyprotic means there's at least 2 or more acidic hydrogens. And down there at the bottom, I have 2 examples. Sulfuric acid is H2SO4. Both of those H's are ionizable, so that means they're both acidic. And the next one is called arsenic acid. Arsenic acid is a triprotic acid. It has 3 acids, 3 H pluses, which can be ionized, so it can create a lot of acid if possible. And the polyprotic acids and the monoprotic acids can be strong or weak. So you can see HCl is a strong acid, while HF and HNO2 are weak. And down there in the bottom, technically H2SO4, the first acid, H plus especially, is incredibly strong. So that would be considered a strong acid. The H3ASO4 is more likely weak. So it can be weak or strong, it's hard to say, but they are going to have a different effect on your reactions. Here's a reaction that shows what happens with a triprotic phosphoric acid. Now, phosphoric acid is H3PO4. So, for example, H3PO4 reacts with water. It makes the dihydrogen phosphate ion, H2PO4-, and hydronium. So, the first Ka, which we'll call Ka1, products over reactants, would be hydronium times dihydrogen phosphate divided by the phosphoric acid, and this value comes out to be 7.2 times 10 to the minus 3. Don't include water because it's a liquid, etc., but this would be the first acidic hydrogen. But phosphoric acid has another acidic hydrogen. H2PO4- can also react with water to make hydrogen phosphate and hydronium as well. So again, remembering not to include water, Ka2, hydronium times the hydrogen phosphate divided by dihydrogen phosphate ion. Notice the Ka for this one though, 6.3 times 10 to the minus 8th. Now as the K values get smaller, you end up with more reactants than products. So the first Ka is bigger, you're going to have more hydronium. And the second Ka here is not as big, so you'll have less hydronium. But this crazy thing even goes on to have a third acidic hydrogen. This is Ka3. So it'll also have some kind of conjugate base, in this case phosphate, times the hydronium concentration divided by the acid hydrogen phosphate. Ignore the liquid water, 4.2 times 10 to the minus 13. So you see here what's happening to the Ks. The first K is the strongest, the second K is usually weaker, and the third K is quite a bit weaker. So usually what happens in calculations, chemists just focus on the first Ka because that's the only one that has like a lot of punch to it. But on the right conditions, you can get the second and even the third hydrogen to come out. Just kind of realize that it's possible. Here are more examples of different polyprotic acids. Oxalic acid has two acidic hydrogens, the one on the left and the one on the right there, and there's their Ka values. Sulfurous acid has two acids. Phosphoric acid we saw has three. Arsenic acid we saw a little bit earlier has three acidic acids. Carbonic has two. Hydrosulfuric acid actually has two, although the second one is so weak people wonder if it's really an acid at all. But anyway, there are also what they call dibasic and tribasic systems. A dibasic system would have two hydroxides. A tribasic system would have three hydroxides. And that would be different, of course, from a monobasic system like sodium hydroxide, potassium hydroxide. Here's an example of a diprotic acid. It's actually ascorbic acid, vitamin C, and it's got a long formula, so I'm just going to abbreviate it H2ASC, all right, where the ASC is the ascorbic acid. It's a pretty long formula. But anyway, there's the Ka1 and the Ka2 values, and again, note that Ka2 is a lot smaller than Ka1. Well, we can calculate the pH of a 0.050 molar ascorbic acid solution using this information. And what we'll do is we'll first find the hydronium from Ka1. We'll then also figure out the hydronium from Ka2, and ideally we'll add them together to give the overall hydronium, and then minus log of that will give pH. Now, in all of these, 100 times K is going to be less than C. So hydronium really is just equal to the square root of the Ka we're looking at times the Ca, and I'll show you that here in a sec. You can find hydronium from Ka1, you can find hydronium from Ka2, add them up to find the pH. So for the first Ka, the first acid that comes off, Ka1 will be the products over reactants, like all equilibrium constants. Now notice on the bottom we have the diprotic version of ascorbic acid, H2ASC, and on the top you have the conjugate base, which is basically the same thing as the acid but without an H+. So it's HASC- times hydronium, and that equals Ka1, which is 1.0 times 10 to the minus 5, which equals X times X divided by the concentration 0.050. So X here is going to equal the hydronium, but also notice here that X is going to equal the concentration of the conjugate base, and that'll be important to us here in a second. So square root Ka times Ca, you end up getting the hydronium, 7.1 times 10 to the minus 4. Now, the second one, we have to be a little tricky because the hydronium from the second part is going to be the hydronium from the HASC minus, all right? It's already lost one H for Ka1. We're dealing with the hydronium from the HASC minus, the second one, and that's going to equal the square root of this new conjugate times Ka2. So notice here that we're using the same hydronium value from the first one, 7.1 times 10 to the minus 4, because that equals not only the hydronium, but it also equals the concentration of the conjugate base, which is the acid now in this part. Whoa, kind of crazy. But anyway, if you realize that, then square root Ka times Ca, the new Ka is 5 times 10 to the minus 12. The new concentration of the acid now is 7.1 times 10 to the minus 4. Throw this in your calculator. Hydronium, 6 times 10 to the minus 8 moles per liter. So the best way then to find the total hydronium and to find the pH then would be to add those two numbers up. So you want to add up the hydronium from the first one, 7.1 times 10 to the minus 4, and add it to 6 times 10 to the minus 8th molar for the second one. Now, with sig figs, you have to cut it off at the largest doubtful digit. And in this problem, when you're adding, that's going to be the 0.1 times 10 to the minus 4. And notice that the other number doesn't even begin until 10 to the minus 8th. So what this means is adding those numbers together, we don't have the sig figs to call it more than 7.1 times 10 to the minus 4. We have no confidence in the numbers to the right of the 7.1 and 7.1 times 10 to the minus 4. So hydronium basically equals the first hydronium from the first part, pH minus log the hydronium from the first part, 3.15. The second acidic hydrogen didn't contribute anything to the pH. It was so small relative to the first one, it's almost like not interacting at all. And this is what we see most of the time with these polyprotic acids. Usually the second acidic hydrogen doesn't contribute anything to the first one. It's so small. If you just focus on the first one, you should be good to go.